Okay, so welcome to the Coastal Resilience webinar series. Thank you for coming. We do once a month. We meet once a month for our joint webinar series. In this seminar series, we explore from very technical case studies to real-world solutions. And our aim is to show how to protect and restore coastal ecosystems. In each session we had in the past and we will have in the future, we feature leading researchers, educators, and practitioners. And like today, we feature also young ocean professionals. So we are within the United Nations Decade of Ocean Science, and which has, challenges and outcomes. We contribute especially to increase community resilience to ocean and coastal risks, and to build as an outcome, a safe ocean. The decade is running very smoothly and very successfully. It has many programs, 50 programs, 300 projects, and different kind of contributions and activities. So it is really, and 60 countries contribute to it. It's really a novel decade of ocean science, which I hope you will continue to follow with us. So our Decade Collaborative Center is part of a partner alliance network composed of University of Bologna, with hosting the secretariat of the Decade Collaborative Center for Coastal Resilience. You find it on your left, the top left. And our partners are CMCC, the Climate Foundation in Italy, and Deltares from Holland, the Netherlands, sorry. And you can follow them with the QR codes. Today, I'm very happy to introduce to you Dr. Federica Borile, who is a researcher at the University of Bologna. And she tackles several hard problems. One of them is the sea level and the sea level rise. And the sea level rise in a limited area of the world ocean where we work, the Eastern Mediterranean. And she will show you the role of water budget on this. Federica has had a master's degree from University of Bologna in physics of the Earth system, and then she earned her PhD with a joint program between the University of Bologna and CMCC, and working on the global ocean circulation, trying to find the impacts of internal tides and Atlantic meridional overturning circulation, which is one of the hot topics at the moment. She is doing her postdoctoral research at the University of Bologna, and she will work, and she is working on constructing a new Mediterranean sea reanalysis. So, to conclude this short introduction, I just wanted to iterate again that we have a question and answer session. So your questions should be input to the question and answer module. And then I will ask your questions to Federica at the end of the webinar, reading from your questions. And we are recording this webinar for other people to follow later. So, yes, we'll talk about this later. And so I welcome Federica. The floor is yours.
Thank you, Nadia. I can share my screen. Okay. Can you see the screen? Okay, so good morning, good afternoon, everybody. As Nadia has just mentioned, today I present our work about the decadal slowdown of the mean sea level in the Eastern Mediterranean Sea, focusing on the role of the water budget. So the motivation that drives our work are many. First of all, now we have more than 30 years of satellite altimetry data that are available to analyze how the sea level has changed in the last 30 years over the globe and in specific regions of the ocean. We, from the literature, we know that the decadal timescales, the decadal variability of the global ocean has an influence on the sea level trends, and the water cycle at the global scale has a decadal variability that is important to compute the proper sea level trends. And more than that, we know that the same temporal scales of the feature of sea level, so the decadal temporal scales are more very important in the Mediterranean basin, where the mean circulation and the water mass formation events has a strong decadal signal. So these three main motivations drives to the main question we wanted to address, which is, does the Mediterranean Sea and the Eastern Mediterranean in particular mean sea level have a decadal trend that is changing over the last 30 years? So in this work, I will present the results from 1993 to 2022. And from the literature, we know that there are big differences from the global scale to the Mediterranean scale, because the global mean sea level trend reported in the literature by Guerrero et al. In 2023 is quantified as 3.3 millimeter per year, whereas in almost the same period analyzed by Meli et al. In 2023, so in the same year, the Mediterranean mean sea level trend is slightly slower, quantified to 2.1 millimeter per year. So the Mediterranean Sea is rising slower compared to the global ocean. And this is evident even if we look at the average sea level over the global ocean on the left and the average sea level computed over the Mediterranean region on the right. These are two indicators provided by the Copernicus Marine Service information. And you can see how the time series that was starting from 1993 is different from the global to the Mediterranean case. The global ocean is rising with a trend reported in this plot around 3.4 millimeters per year and an acceleration of 0.11 millimeters per year squared. And the time series is quite small since it includes a large domain, a huge domain as the global ocean. But if we focus just on the Mediterranean Sea, the time series on the right shows a larger variability in time. And we're not still able to recognize an acceleration of the sea level from this plot. So in the presented work, I will focus mainly on three different decades from 1993 to 2002, from 2003 up to 2012, and the last decade, which is the most recent that we analyze, is from 2013 to 2022. These 3 decades are not overlapping from each other, but we can see the differences both in the Mediterranean, the entire Mediterranean basin, and we will analyze also the differences between the western side of the Mediterranean and the eastern side of the Mediterranean, focusing for a while to what happens in the Adriatic Sea, which is a very peculiar case for the decadal sea level trend in the Mediterranean. Talking about the data sets we use in this analysis, we use most of all observational data sets, sorry for the typo, to compute the decadal trend. We use satellite altimetry data of the daily sea level anomaly from 2 different data sets. The first data set is called hereafter CMS, which is an all-sat product at 1/8 degree of resolution in the European area. The aim of this data set is to better reproduce in the best way the mesoscale variability of sea level anomaly in the European area. And in order to do that, they combine together the information coming from all the available satellite altimetry missions that you can see on the in the figure on the top right, where you have a time series and each bar corresponds to the lifetime for a satellite mission. So we have a lot of satellite altimetry missions that have been worked in the past and that are still working and that are planned for the future years. The second data set we use is called hereafter C3S, and it has a global coverage at 1/4 of a degree of resolution, and it provides again daily sea level anomaly at the global scale. This dataset has a different goal because it is specifically designed to ensure the homogeneity and stability of the global and regional sea level sampling rate. So it has a different goal compared to the CMS dataset, but it ensures that no biases are added to the sea level trend computation due to the number of missions we are considering. This dataset just focus on the reference satellite altimetry missions. So we think it's more reliable for sea level trend calculation. And then we use also in situ tide gauges data to validate our result in the specific case of the Adriatic Sea. And the data comes from the permanent service of mean sea level dataset. In order to analyze and to understand which are the contribution of the observed sea level trend, we computed the water budget. And the dataset we use come from different reanalysis datasets that are ocean reanalysis, atmospheric reanalysis, or hydrological reanalysis according to the case. I will explain you better into the detail during the presentation. So coming to the method we use to compute the decadal mean sea level trend, first of all, we chose which is the region of interest. So as I said before, we analyzed the Mediterranean entire basin, the western and eastern side, and the Adriatic Sea. And we compute for each of these the special average of sea level anomaly. So we compute the sea level anomaly basin mean, and we obtain a time series for each of the basin of the area of interest. For each of them, we also remove the daily seasonal cycle to obtain a this season at sea level anomaly. And in this plot, you can see which is the seasonal cycle. So how does the sea level change through the year from summer to winter, where we have the peaks reported here. And you can see that the range of the seasonal cycle for the sea level in the Mediterranean region is around 16 centimeters. And it is slightly different from 2 datasets we used. So from C3S to CMS, the seasonal cycle has a bias, an offset of around 1 centimeter And then once we removed the seasonal cycle, we obtain a time series of sea level anomaly that has still to be slightly, let's say we have to work on that, because we focus on time scales that are larger than a year. So we remove short-term fluctuation, extreme events on sea level signal that can affect the multi-year trend we want to compute. So we apply a low-pass filter in the frequency domain to remove such extremes. And the final result is for the entire Mediterranean basin, the following time series. You can see the 3 different decades with different colors, and overlying the blue, the black curve, which is the original data set. This is just to show how we filtered out the extreme events of sea level anomaly. How we compute the decadal trends over 10 years sliding windows, we use the Townsend slope method, which is less sensitive to outliers compared to the traditional linear regression method. So again, we want to just understand which is the decadal behavior of the sea level in the region of interest, not affected by extreme events. And then we compute its uncertainty using the stationary bootstrap scheme. But more of that, we quantify the statistical significance of the result we obtain using the Menckendal test. And moreover, but I will not go into the detail of this, we also quantify the differences between the decadal trend we obtained using the Wedge test. So this is the time series of the decadal trend of the seasonal sea level anomaly in the Mediterranean basin. You can see 2 different time and 2 different lines for each decade, data set. And the C3S, the blue line, is the one that gives us much reliable results in terms of decadal trend. But as you can see from now on, also the second data sets provide almost the same results. So it's much more, our results are robust. We have each dot here represent a decadal trend computed over a time window of 10 years. So for example, 1998 value represent the trend computed from 1993 to 2002. So we can see immediately how large is the temporal variability of the decadal trend, with the largest values in the middle of the time series. Whereas in the last period, so starting from 2016, we have a slowdown of the overall Mediterranean mean sea level trend, decadal trend. And starting from 2008, the 2 datasets slightly shows different results. And this is due to the fact that a large number of satellite missions were available from that period. So the bias induced by combining together different mission datasets increased in time. That's why I mentioned before that C3S is the most reliable dataset for our analysis purposes. The 3 non-overlapping decades are highlighted here from the circles, and you can see also the uncertainties of the values. And if we just focus on these 3 values, we can say that the decadal trend over the entire Mediterranean Sea is almost the same. Always above 2 millimeters per year, but below 4 millimeters per year. But if we have a look on the map, so how different points of the Mediterranean Sea contribute to the overall mean sea level decadal trend, we can see big differences. Here you have the first decade of decadal trend on the left, the second decade in the center, and the last decade on the right. And you can see how the Western Mediterranean during the first decade has a weak sea level trend and slightly increased over time up to the third decade, where it has larger values compared to the eastern side. And the Eastern Mediterranean behave exactly at the opposite, with larger trend values at the beginning and smaller trend values at the end, with the decadal trend that turns also to be negative in the marginal seas of the Adriatic and the Aegean seas. We have a very strong negative region of sea level trend during the first decade in the Ionian Sea, but it is due to the Eastern Mediterranean transient event, which is well known in the literature, and it disappears during at the beginning of the second decade, and that's why it also disappeared from the sea level signal. Everything is presented here is totally smoothed out if we just compute the entire 30 years trend of sea level in the Mediterranean, as you can see in the map on the bottom. So the 30-year trend oversimplifies the representation of the Mediterranean behavior at the regional and local scales. We have a value that is 2.4 millimeter per year, which still, as we mentioned before, is lower compared to the global mean sea level trend over almost the same period, which is 3.3 millimeter per year. So now let's focus on the contribution of the two different sub-basins of the Mediterranean Sea. On the top, you have time series of the decadal trend of the Western Mediterranean, and on the bottom, you have the Eastern Mediterranean. Both of them have a similar behavior during the first period of the time series, but then starting from 2008, they start to diverge. The Western Mediterranean increase, the decadal trend is still rising faster, whereas the Eastern Mediterranean is slowing down more and more, with a minimum value of almost zero, so almost a negligible trend value around 2015. So since in the previous plot of the entire Mediterranean basin, we show a weak slowdown in the Mediterranean in the last period of the decadal trend. Here we can see how the slowdown at the basin scale is driven by the Eastern Mediterranean behavior. And again, if we just focus on the blue line, which is the C3S satellite dataset, we can see that the slowdown in the Eastern Mediterranean started from the decade around 2008. Zooming in the Adriatic Sea, we can see here how drastically the sea level decadal trend changes through the 3 decades. We have strongly positive values, which are higher than 6 millimeter per year during the first decade, that drops down to negative values, that are statistically relevant over almost the entire region during the third decade. I talk about statistically relevance because it means that just where you can see small dots, our analysis said that the value, the trend that we compute can be at least around zero, can be negligible. So wherever we do not have dots, we know that the negative trend values are reliable. And this is the plot as the ones I showed you before, but just focusing in the Adriatic region. You can see how the slowdown is marked starting from 2010, and how much it becomes negative during the last period. And these results are confirmed from in situ data, so from tide gauges information. And we compare them looking at Trieste and Venezia tide gauges. Unfortunately, for both of them, we do not have the entire period of data. But again, just focusing where we have the complete time just focusing on the decades where we have the complete time series, we can see that the differences, especially from the second to the third decade, is consistent with what we showed in the previous slide. So in this table, you can see how the satellite data drop down from strongly positive sea level decadal trend to negative sea level trend in the third decade, and the same behavior is observed both in Trieste and Venezia. So now let's move to the most interesting part from the scientific point of view of this work. So the analysis of the mean sea level equation balance. From Pinardi et al., which is our reference in 2014, we have a mean sea level equation that is valid for any laterally open region of the ocean, and where we have the tendency of the total sea level, which is the left-hand side term in this equation, that is due to the balance between different terms on the right-hand side. We are talking about the mean sea level, so these terms are averaged out over the entire region of interest. And we have the first term on the right-hand side, which is the volume transport at the lateral open boundaries of our domain, meaning that we have a volume of water that may enter or exit through the open boundaries of the region of interest. We have water fluxes at the surface of the ocean due to surface processing. And this term is the combination of the evaporation, so loss of water from the ocean to the atmosphere, precipitation, which is a gain of water from the atmosphere to the ocean, and river runoff. Then we have the steric term, which is the so-called steric effect, that is the tendency of the steric sea level that is the contribution to the total sea level due to the compression or expansion of the water column due to differences in temperature or salinity content of the water. And finally, we have the density flux in or out of the domain at the open boundaries. The quantities that interest the water properties, meaning that the temperature, the salinity of the water to compute the steric effect, and the volume of water that is entering or exiting to the from the region of interest, are computed using the ocean reanalysis method REA24. And we use daily data at 1/24 degrees of resolution. Whereas the quantity, the field that come from the atmosphere, meaning that evaporation and precipitation, are computed starting from the dataset of ERA5 reanalysis. And finally, the river runoff information comes from the hydrological reanalysis EFAS version 5, which is a river discharge dataset at very high resolution, both in time and space, provided by the Copernicus Marine Service dataset. According to the literature, the last term I described before, so the density flux, is negligible in most of the cases. And from the literature, we know that this term is negligible also for the Mediterranean case, so we will focus just on the first three terms hereafter. Start with the steric compensation component. As I said, the steric sea level is the contribution to the total sea level due to the variability of temperature and salinity of the entire water column. And in this plot, you can see how the tendency of the steric component is fluctuating over the entire period of our interest in around zero. So we will see in a while that its contribution is negligible to the overall water balance at the basin scale. And this is due to the compensation that has been reported by Meli et al. In 2023, and here it's confirmed, due to the fact that even though the temperature of the water is on average increasing in the Mediterranean Sea, as well it is in the global ocean. In the specific case of the Mediterranean Sea, we have a salinization of the water column, meaning that increasing the salinity, the allosteric component of sea level is compensating. So we have a contraction due to the increase of salinity and an expansion due to of the increase of temperature of the water column. So they balance each other, and the net contribution to the overall water balance is negligible. Here we have a look to the surface water budget. So the balance between evaporation, precipitation, and river runoff at the surface of the ocean. You can see that in this plot you have the values associated to the entire Mediterranean basin. We have an increase of precipitation from the first to the second decade that slightly decreased during the third decade, but not so much. So definitely we have a strong increase of precipitation from the very beginning of our time series to the rest of the time series. And the same is for the precipitation we have, which is this middle light blue line bars. We have an increase on the precipitation values, but not so much to balance the change in evaporation. So the net, the balance between the evaporation and precipitation and river runoff, which remain almost the same over all the time periods, is to have an increase of the surface water contribution, as you can see by the orange bars, which are increasing their values from the first to the third decade. So the changes in the surface water budget are driven by evaporation, and the same comment can be applied to the Eastern Mediterranean basin, which is the main focus of our work. Again, we have a strong increase in evaporation, which is not offset by balanced by precipitation. And the river runoff is almost constant again. Talking about the lateral transport, we have lateral transport at the Gibraltar Strait. We have an open boundary at the Gibraltar Strait and at the Dardanelles Strait. But if we just want to focus on the Eastern Mediterranean basin, we have an open boundary at the Calabrian section that we fix at 16 degrees east. This is a very large open boundary where lots of dynamical processes and dynamical features comes in and out of our domain of interest. So the uncertainty associated to the lateral transport across this section is very high. But for sure, we know that what happens at the Gibraltar transport is not just a matter of what happens locally there, but the changes we observe at the Gibraltar transport are connected to changes in the dynamical structure of the larger North Atlantic domain. So finally merging all this information together, again, we have a look to the overall equation to understand how each contributor can have a role to the overall tendency calculation of the total sea level. And you can see here, again, on the Mediterranean, entire Mediterranean basin, that we have a balance between values that are very large, and the difference is, so the main, the balance is just interest small values that are very, very small. So it's quite difficult to catch the proper balance using different data sets. But this is the best that we can do. And here you can see that the main contributors are, again, the lateral transport, so the first term, the green bars, and the surface water budget, which are the yellow orange bars, whereas the stereo component has a negligible impact to the overall balance, and the net total sea level tendency is very, very small, small values around 0, 10, 30. So again, we have a decrease. Looking just at the net values, we have a decrease of the tendency of total sea level, and this is due to an increase evaporation, so negative values of sea level surface fluxes that is not balanced by the lateral transport. And the same can be observed just focusing on the Eastern Mediterranean. We have negative values of surface water fluxes that are increasing in time from the first to the third decade, and differences in the lateral transport that are not able to offset the observed evaporation increase. So finally, the concluding remarks is that during the last decade, we analyzed the Western Mediterranean tends to increase the sea level, the decadal sea level trend in agreement with what has been observed at the global scale, whereas the Eastern Mediterranean tends toward negative values trend with the smallest values observed in the Aegean marginal seas. The mean sea level slowdown is due to a combined effect of changes in the water budget and compensation between thermal expansion and haline contraction. But the key driver is the increased evaporation, which is not compensated by the other terms that play a role in the mean sea level balance. And that's in order to understand and to obtain reliable values in the analysis we propose here, we stress the importance on provide a continuum monitoring at the regional scale of the components of the water balance. And this is essential to improve climate projection and how we can understand the peculiarity of the Mediterranean Sea. But finally, the most important take-home message is that if we just talk about the long period decadal trend, which is much more larger than the decadal values, we have to be aware that the multi-decadal timescales oversimplify the Mediterranean behavior. And if we want to provide values that are useful for climate adaptation strategies in the coastal areas, we must be very aware that decadal fluctuation can be strongly change the long-term value we provide and can make a difference in the period of interest in each specific case. And that's all from my side. I thank you all. And all this work has been deeply described in the paper we recently published in Frontiers in Climate. So for any further information, please don't ask me or let's read the paper. Thank you.
Thank you, Federica, for the nice.
You can non togliere il microfono.
Okay.
Il microfono anche, teniamo aperto solo il tuo.
Yeah, okay, now we are all set. So thank you for the nice presentation on this very delicate issue of sea level rise, which stresses our capacity to adapt to climate change in the Mediterranean Sea. We have two questions. The first one is, do we know anything more about the lagoons of Nador or Ceuta in the Western Mediterranean from this data set?
Well, these data sets do not go exactly up to near the coast. They are not near coast product. And we need to analyze much into the details, the tide gauges, so in situ data to understand better what happens inside the lagoon, so in the peculiar places where small scale dynamics can have a larger impact compared to the basin scale analysis. But in the presented work, we do not mention, we did not go into the detail of the Western Mediterranean, but this is something that is still in, let's say, work in progress, because we want to analyze exactly what happens in the Western Mediterranean, exactly along the coast. So we will have results published, I hope soon, about that.
So in fact, the second question is, it says, thanks for the interesting presentation. Have you compared the C3S sea level anomaly values with tide gauges in the basins?
Well, we do not have, for my knowledge, we do not have tide gauges in the open sea, let's say. We just have information along the coast, and we just provide in this presentation, I showed you just 2 tide gauges, but in the paper we mentioned also a 3rd tide gauges along the Israel coast. But we did not compare more. We just focus on these 3 locations because we have an issue to have a temporal coverage over 30 years on tide gauges. So in situ information is quite sparse in time. It's difficult to have a continuous time series to suitable to compute the Decadal trend.
Yeah, but in the Western Mediterranean, you have other long time series.
Yes, that's why we want
to do this.
Yes, but on the eastern side, so on the Eastern Mediterranean, we didn't.
Yeah. So I don't see any other question. And yeah, I've already asked. And so, well, okay, no more questions. And I would like to thank again Federica for this nice work that points out to some hidden processes.
There's a new question.
There's another question. Oh, good. Yes. So given the relatively short time series, 1993-2022, how confident are you in drawing conclusions about decadal trends and sea level rise in the Mediterranean?
Well, using just 30 years, we cannot say recognize decadal, let's say, fluctuations, where it's hard to recognize the entire, let's say, wavelength of the oscillation, but still we can see what we learn from this work is that we must be aware that there are differences from one decade to the other. We're not able to analyze, to recognize a decadal dominance of the decadal frequency that is dominant in the sea level trend analysis, but at least we must be aware that there are differences from one decade to the other. So just looking at the entire time series may not be convenient to set let's say, a plan of coastal an adaptation plan at the coastal in the coastal regions, because it may be strongly different from one decade to the other. The sea level trend may be double or half, depending on the period, the smaller period you are interested in. So just not taking into consideration the 30-year, the long-term trend, but be aware of the differences at shorter time scales, because they make the difference, even though we cannot say anything about proper fluctuation at the decadal scale.
And then here is another question. How do you expect the slowdown will evolve in the near future?
Well, again, this is a work in progress, so good question, because we may expect that the slowdown we observe here may just stop, at least may become weaker, and the sea level trend may rise again, increase again. And this is what we observed from the most recent analysis or the update of this work. So especially in the Eastern Mediterranean, we expect to have, again, an increase of the sea level trend. And this is a good chance to recognize a fluctuation, as I said before, just not the variability, but something that is repeating in time. But we will see. I expect to have an increase again of the sea level trend.
So how does the decadal slowdown in Mediterranean sea level rise compare with global sea level trends over the same period?
This is something I mentioned at the very beginning, but maybe it's good to stress it more. We have the Mediterranean sea level trend that is smaller compared to the global scale. So we have 2.4, 2.5 millimeter per year in the Mediterranean compared to 3.4 at the global scale, millimeter per year. But the main difference is that at the global scale, we have a smoother time series of sea level that allows us to recognize an acceleration of the sea level trend, whereas this is not the case for the Mediterranean. The variability is too large.
In fact, there is another question is, could this divergence, the difference between the global and Mediterranean, be due to regional oceanographic phenomena?
Yes, for sure, the Mediterranean is smaller, so the dynamics, the ocean dynamics within the basin play a major role in the Mediterranean case compared to the entire global ocean, where different regions, so different behavior at the regional scales are averaged together and may balance each other. Whereas in the Mediterranean case, we saw there is difference between the western and the eastern side, but still the dynamics of what happens within the ocean can be relevant. And it's most of all what happens on the eastern side may affect with an offset in time the western side and vice versa. So for sure, the dynamical process has a larger impact in the Mediterranean case.
I must say, the global ocean has no straits, has no transport.
Has no transport at all.
Has no transport at all. So that's a big difference, and that's regional oceanography. So thanks, Federica. Then we have another, so is it possible that the slowdown observed in the past 3 decades is a temporary fluctuation, with the long-term trend still pointing toward an acceleration in sea level rise as seen in other regions globally?
Yes, it could be. Since the variability in the Mediterranean basin is larger, we need a longer time series to observe an acceleration. We cannot just trust on 30 years to recognize a net acceleration, as it has been done in the global case.
So does vertical land motion have a role in masking or exaggerating the observed sea level trend fluctuations in 2 regions of the Med?
Well, the land motion for sure has a role when we look at local data, so in situ information type gauges, and we need to take into consideration subsidence, isostatic adjustments, or the impact on variability on the land reference height at the local scale. But at the basin scale, I don't think the land motion may have at the basin scale, looking at the satellite, yes, we have, I mean, the satellite data does not take, has a different reference compared to land. So it just take the measurement from satellite to the reference geoid, which is not offset by the land movement. So for sure, satellite does not have to take into consideration in the open ocean of the land movement of land.
How should policymakers and coastal planners in the Mediterranean region approach the decadal slowdown of sea level rise, given the uncertainty surrounding trends in such a short time frame? Should they consider more conservative projections or prepare for potential acceleration?
Well, it's a difficult question. I wouldn't take into consideration the acceleration at the Mediterranean scale for the reason mentioned above, but I would say that they must be aware that the long trend values may be just an information that has to be applied to the specific case. So it depends on the plan they want to address. If we want to address to make a plan that is at 50 years, that is valid for 50 years, for sure the 30-year trend may be a good value to trust and to use as a reference for the make a plan, adaptation plan or whatever. Whereas if the plan has to be relevant at year with a return period of years, well, the uncertainty is big, as I mentioned before. So the decadal sea level trend uncertainty is quite big, but just at the time being, we are not able to provide a specific value for each location to be used by stakeholders, let's say. But we just say, be aware that the general value cannot be so good to be used as a specific valid in each point. Just maybe additional studies are required to address which is the most reliable value in the specific place we want to act.
And in fact, another question is not a question but a comment, is I think we should use precautionary approaches given the high uncertainties.
Yes.
So yes, and definitely we should use the global value, I would say myself. We shouldn't use a global value to do projections if projections use the global values at the coast. So using a global value at the coast may be problematic.
Yeah, if we want to be locally effective, if we want to obtain good results at the local scale, we have to use local information so that are valid at the scale of interest, not just at the global scale, because different regions of the ocean, we have, for example, the Baltic Sea, where the sea level trend is decreasing and it's becoming negative. So the global ocean value at all is not valid there, but we are the Mediterranean case is something in the middle, but still we need to be careful to use the global value for sure.
Okay, I think we are almost there. Thank you, Federica. Lots of questions. Very good. Thank you to the listeners and the participants. Thanks for the questions. Very nice. And we have the last, the last slide to announce the next webinar by Dr. Virginia Tassin Campanella. She's from an international law firm dedicated to ocean and seas. We're very interested to hear this. This is, we are in the holistic coastal resilience part and looking forward. I hope you will join us. Thanks a lot and have a nice remaining day. Bye.